Okay, so let's look at the magnitude of a vector. So first question, or just a reminder, that a vector has magnitude and direction. So when you graph it, that will show the direction. When you're given the coordinate or the component form, that tells you the directions. Column vector, that tells you the directions. And then we need to calculate the magnitude. Okay, reminder from yesterday, could be the absolute value symbols or double absolute value. So the first one, given vector v, represent it with a geometric vector. So just sketch that. It's kind of nice to have a straight edge for this unit. So buy a ruler, if you never have in high school yet. Do it before grade 12. Now, if you have a little bit older version of a calculator that doesn't plug in, then my trick is the battery cover is a straight edge. Never going to have to measure anything. You just have to be nice. So straight edge. That's my trick. In any case, we are doing 3i and 6j. So there's vector v. Oops, I wanted. Okay, so that's a geometric vector because I graphed it. Magnitude, well, that's a right triangle, right? So that's 3 and that's 6. So the magnitude of v is the square root of 3 squared plus 6 squared. Okay, and represented as an exact value in simplified form. So 36 plus 9 is 45. That's 3 root 5. Okay, we don't use units unless it's an application question, right? So just leave it as 3 root 5. So what did we do there? We used the Pythagorean theorem. Pythagorean theorem was the x-coordinate squared plus the y-coordinate squared. Same thing, it doesn't matter what quadrant it's in. If you're squaring a negative, so say the x value is negative, you still get a positive, right? So you can just use the coordinates. You don't have to graph it. You don't have to change the sign or anything like that, because when you square a negative, it's a positive. So vector OA, there's the component form, there's the column vector form. Magnitude of it is the square root of the sum of the squares of the components. 2 dimensions, 3 dimensions, sum of the squares of all 3 components. And really, if you go back to Math 10, when you did trig, Pythagorean theorem and trig, you did some double triangle questions. Really common one that we give is you've got a cliff and a river, and you have to figure out the height of the cliff or whatever, and you know the distance down the river. So you form a right triangle that's flat, and a right triangle that's in 3 dimensions basically, and you have to find the missing side. It ends up being the same thing. Okay, so you can look for the development of that, but we've actually already done that back in Math 10. So those are vectors that start at the origin. If you have vector AB, you want to find the equivalent of starting at the origin. So you subtract vector A from vector B to get the components of it. And so really, you're finding those values and squaring. It's the same formula. I always do that first and then put it into the magnitude rather than showing subtracting in there. It gets pretty messy. I do all this stuff first. Okay. All right, so let's just practice. These are pretty straightforward. It's a 3-dimensional vector, square root of each component, so So 3 squared plus negative 1 squared plus 5 squared. And simplify it if you can, but no decimals. Only time decimals is in application questions. Okay, so that's root 35. Given vectors u and v, find the magnitude of 2u minus v. So I'm going to find what 2u minus v is. First, I'm not going to put all of that underneath the radical, right? So this 2 times this, that's going to be 4 minus 1 is 3. Negative 10 minus 4 is negative 14. So now I'm finding the magnitude, of 3 negative 14. Okay, so you can even show it with big absolute value symbols around a column vector. Let me just check if oops. Thank you. This is a typo. I think because it was A3 and I put 3 in. So that should be a 2. So change that in your notes, please. Oof. Thanks for pointing that out. Okay. So make sure you change that in your notes. Thank you, thank you. Okay, so sometimes we'll want to find a unit vector. So what is a unit vector? Unit vector is a vector that has a magnitude of 1, okay, in the same direction as the original. So you basically, you've got a vector, say it has magnitude of 5, so 5 units, you're drawing one in the same direction, but it has a length of only 1 unit, okay? So how do you calculate that? Well, first of all, if it has 5 units, you're going to divide by 5 to get the new magnitude. And it has to be in the same direction, so the ratio of your x and y components, or x, y, and z, has to remain the same. But really what you do is you divide your vector by the magnitude of it. Or, as it's shown here, 1 over the magnitude of the vector, so that's a scalar, times the original vector. And the notation is this little kappa, right, a little hat. So that means a unit vector. So the unit vector of v can be found by multiplying v by 1 over its magnitude. So determine the unit vector in the same direction as v here. So I want to find the magnitude of v first. So 3 squared plus negative 4 squared. That works out nicely. It's 5. So v cap, so the little hat there, is equal to 1/5 times 3i minus 4j. And if we expand that out, that's 3/5 I minus 4/5 j. Okay. Now, there will be times where you're actually not going to multiply out that 1 over 5 into the vector, or into the column vector. You might leave it out front. You're kind of going to, for now, we're going to multiply it through, but when we get to some applications and some questions where we need to use the unit vector, we might find that we will leave it out front, okay, as a factor. Magnitude of view. One thing that we don't do very often is actually rationalize. So for one time, like we've been telling you to rationalize denominators for 3 years now, but sometimes with this we don't. So u kappa here is 1 over root 30. Certainly you would simplify that, root 30 if you could, you can't. So sometimes we just say leave it like that, okay? And if I wanted, what you need to be able to do is look and see if this, say this simplified to 2 root 30, then you might want to multiply it in, so you can simplify some of them, but I would accept this unless I specify express as an entire vector, something like that. So either way, particularly, so if it ends up being irrational, you can multiply easily in, even if you get fractions, but irrational, we actually keep it in that form a lot of times, okay? So just be aware of that. We're not quite as picky about simplified form. Okay, next one. Obviously, this is not a unit vector right now, okay? It says determine a vector in the same direction as vector u, but with magnitude 5 root 10. So it has to be in the same direction. So the new vector that we get has to be some scalar multiple of this. So first, figure out what the magnitude of u is. Because that's, you need to know that in order to compare it to the new one. Okay, and you can simplify that. So 2 root 10, and we want it to have magnitude of 5 root 10. So our k value, or our factor that we want to multiply that, I'll call it k, is really 5 root 10 over 2 root 10. Okay, so this would be k where ku equals our new vector, we'll call it. Okay. So we'll call this vector v. So we take the magnitude of v, divide by the magnitude of u, and get 5 over 2. So that means our v will be 5 over 2 times negative 6, 2. Now this one, I am going to multiply in because look, you can simplify it, right? So here, that's going to be negative 15, and that's going to be 5. And check it. What's the magnitude of negative 15, 5? So 225, that's 250, that's 5 root 10, you got it. Okay, so you can always check. All right, next thing is what's called the scalar product. I actually call it the dot product a lot because when I learned it, and I used to teach in Ontario, we did vectors in grade 12 there, and we called it the dot product. It's also called the inner product, scalar product. IB tends to call it the scalar product. Basically, it's a product of vectors that gives you a scalar. Okay, so you can't really multiply vectors together. this is the closest that you get to multiplying. The reason why it's sometimes called the dot product is that there's a big dot in between. Okay? So it's not craziness. It's a big dot in between, which means you're finding the dot product. Take a look what it is. So if you have two vectors, just look at the column vector form, AB and CD. The scalar product is AC plus BD. Well, what's AC? It is the X components multiplied together. BD is the Y components multiplied together, and you add them up. That's how you get the value of the scalar product. Okay? We'll talk about what it means and in a minute or two. But that's the formula in terms of its components. We'll learn the geometric formula in a minute. If it's 3 dimensions, then it's AD plus BE plus CF. Okay? So it's pretty easy to calculate. So determine the scalar product of each of those pairs. You don't have to copy out each vector again. You can just go V dot W and then do that work in your head. This is what you're actually doing. So when you do that, you get negative 12 plus 7, which is negative 5. Negative 41. Oh, not negative 41. Yeah.
Yeah, there's a mistake on the answer key. I'm just fixing it.
Okay. So next one, before you take the dot product, find those vectors. So 3u plus v. You can distribute, but that takes a lot of time. We'll talk about the properties. You actually can distribute the dot product. This times this, like you would algebra, but then you're doing the dot product 4 times, right? So I actually find it easier to figure out what 3u plus v is first. I gotta fix the answer. This is correct.
It's wrong here. I was doing this last night or the night before.
Okay, so those are just calculations, kind of meaningless, right? You're just doing these calculations. How is that going to help you with anything? So we're going to do this sort of a little inductive reasoning table here to see how some values relate to each other. So get out your calculator, because you will need your calculator for it. What's in the first two columns? Well, the first column is all the same vector. So vector v is 5, 0. So if you were to actually, so I look like this. So 5, 0 looks something like that. Okay, and then this vector here has the same magnitude as v. Okay, all of these have the same magnitude. Okay, so its graph, they're all in the first quadrant in this case. So somewhere in the first quadrant, the magnitude is there. I'll just change the color of that actually. Okay, so magnitude. And so it says calculate the value of the dot product of v and w, rounded to the nearest hundred. Okay, so you can do that. We're going to go through each row at a time. So if we're calculating the dot product, that's going to be 10 root 5. So this will be equal to 10 root 5, which as a decimal is 10 root 5, 22.36 for the nearest hundred. Right? So we were calculating the dot product of v and w. Then it says calculate the value of the angle formed between them, theta, using tan theta, and then the value of cos theta to the nearest hundred. That's why we're doing each row, so that we keep that in our calculator. So if I were to draw a right triangle here, okay, the y, the opposite side, so this point here, for example, would be 2 root 5, root 5, okay? So this is root 5, this is 2 root 5. So to get theta, I said use tan, so we're going to do it in degrees. So check your calculator, convert it to degree mode. Okay, and then we'll go second tan, the y value, root 5, over 2 root 5. Now, if you see, the root 5's divide out. So it really ends up being inverse tan of 1/2. That is actually a special angle. No, actually 1/2 for tan. So we're doing it in our calculator. We need the decimal form anyway. So in this case, root 5, or just do it as a half again. So then 2 root 5. So 26.57 degrees. Now, while it's in your calculator, it says calculate the value of cos of that angle. So now cos of that angle is 0.89 to 2 decimal places. Okay, so just then run one row. Everyone okay with that? In degree mode? Okay, so just remember, if you're dividing by 2 root 5, you have to have brackets around it. Okay, so we're going to do it for each row, but because it's in my calculator, we're actually going to skip a little bit to the next step. Now compare your values in the column v dot w, so the dot product, with this calculation. Okay. Magnitude of B. Well, we already know the magnitude of B is 5. And the magnitude of W is 5. That was given up here. Okay. We have the value of cos theta here. Multiply that then by 5 times 5, or 25. Notice what you get. You get the same value as the dot product. Okay? So what did you multiply there to get the same value? You multiplied the cos of the angle between the two vectors by the magnitude of each of them. So that's really making these equal. Now we just did it for one case. We'll do it for a couple more, but that's inductive reasoning to come up with this. Okay, so the dot product, the geometric form of it, the calculation is the magnitude of each vector multiplied by the cosine of the angle between the vectors. So let's try the next one. Dot product is 15. Don't even need your calculator. Okay, so then theta is going to be second tan of the y value of this, which is 4, over the x value, 4 over 3. So that angle is 53.13 degrees. While it's in your calculator, take the cos of it. You get 0.6. Okay. Now take 0.6 and multiply by 5, the magnitude of B, by 5, the magnitude of W. You get 50. Okay? Get the same value back. So the same thing is going to happen in all of these. You can test, I'm not going to go through all of them, but remember these all had a magnitude of 5. We started from the same horizontal vector. This is your angle theta. Okay? So when those vectors are tails together, the angle is theta between them, and that's equal to the magnitude of each vector multiplied by the angle formed if the tails are together. If they're not together, it'll be a non-acute angle, which is fine. We'll figure that out in a little bit. Okay, so same, you can continue that. Yes, they are the same. Okay, so there's the geometric definition. So this is theta, angle between them, tails together. The tails don't have to be together, but you have to think about what angle that would be if you needed the tails to be together. Okay? So we're going to use that to calculate angles between the vectors. So to summarize the formula here and calculate the angle between the vectors, we'll rearrange. So basically here, if we want any two vectors tail to tail, right, that moves here, okay, that's what it looks like. That's the angle in between it. So how do we determine the measure? Well, what we just learned is this dot product is equal to the product of the magnitudes times cos theta, so we rearrange it. And remember, the dot product in terms of the components is the x components together plus the y components together. Okay, so that's how we're going to calculate. Saying that, we're going to do a bit of a proof here using the cosine law, just so that you're aware of how you can do a proof using the components. Because sometimes in IB, they might ask you to algebraically show a component on an IB exam, a proof of some property of vectors. So this is kind of a good example. So we've got vectors v and w, theta's between it. joined up V and W with vector X. So in this case, joined it with the arrowhead at W. So technically, vector X, that vector is W minus V. Now the magnitudes, it doesn't matter which direction. Okay? But here is your cosine law. Right? That's a triangle. So if you remember back to Math 10, if you know the magnitudes of two sides of a triangle and the angle contained between them, you can find the measure of the third or opposite side. That's the cosine law in terms of this diagram. We don't know the components of x, but we do if we express it in terms of v and w. Okay, so now here's where we're going to actually show some algebraic work to prove it. So here we're going to keep our left side. Actually, yeah, I'll just do it within. I like to keep left side separate from right side, but I'll just do it within here. Now, before I substitute in, I'm going to do my w minus v, and I'm going to use just a 2-dimension because that's what that is. So that'll be w1 minus v1. Okay, where w is so on the left, magnitude of that. I didn't leave a huge amount of space, so try to write a little bit small. Okay, so that's the magnitude of w minus v. Square it. Magnitude of v is that squared. Magnitude of w and we're trying to prove that we can get cosine equaling the dot product in the component form divided by the magnitude. So this I want to keep. I'm not going to expand that out. That's part of what we have here, right? So we're trying to get back into this form. Right now I don't have any dot products in there. So I'm going to keep that minus 2 magnitude of v, magnitude of w, cosine v. Obviously, when you square root, the root signs go away. We're going to need to expand out these brackets. Okay, so the root sign goes away. Squaring that is going to be w1 squared minus 2w1 v1 plus v1 squared. And w2 squared minus 2w2 v2 plus v2 squared. Squared plus v squared. And then you'll notice that v1 squared adds to 0, v2 squared adds to 0, w1 squared adds to 0, w2 squared adds to 0. can divide by -2. And so we get W1V1 plus W2V2 equals magnitude of V, magnitude of W, cosine theta. Okay? Here, the W is first, but W1V1 is the same as V1W1. So oftentimes we show it in the same order. So this is the same as V1W1 plus V2W2. And then we can divide that by magnitude of V, magnitude of W, to give you cosine theta. And that is what the equation was. Okay. So I wanted to go through that just in terms of the components, because sometimes they might give you a property. We'll go through the properties and say, given general case, show that these properties are true. That's what you do. You show the components and do the work for them. Okay, so now let's do some actual calculating. It says, determine the measure of the acute angle between each pair of vectors, rounded to the nearest tenth of a degree. Now I said acute angle because, so these are just vectors. When we get to equations of lines, then for sure there's an acute and obtuse, because lines meet and they cross, right? So one would be smaller than 90, one would be bigger than 90. In this case, actually, they're just vectors. So let's just find the measure of the angle in between them. So just, we'll just do the angle and not worry about the acute. So here we'll do U dot V over magnitude of U, magnitude of V. So that's the formula. You don't have to copy it out each time, but I just did it. It's our first time doing it. So the dot product of each of those, you can just do that in your head, or you can show the two steps. So that'd be 12 minus 14. And then magnitude of U, again, you can do that in your head. You don't have to simplify it, because this is all going in your calculator. This is not your final answer. So 16 plus 4 is 20. 9 plus 49 is 58. So really, theta is going to be inverse cos of -2 over root 20 root 58. Stop. Okay. So we are, oops. It says in degree. So calculators in degree mode, second cos, -2 divided by, and then you can really just do square root of 20 times 58. Then you don't have to worry about brackets. Okay? Here's 10, 93.4 degrees. And so we'll just leave it like that. So that means if you were to graph these, and you can kind of test it, because it's 2 dimensions, it's pretty easy to test. So that would be U there, and then 3, -7 here. Okay, so that would be your angle in between them, 93.4. So yeah, I put acute in there. care. I'm not going to do that because
We don't really care about that with these just vectors. When we get to equations of lines, we will care about acute and not acute.
Okay, so do the next one. It's 3 dimensions, but same process. So really, if I give this on a test and it's not a multiple choice type question, I just need to see either something with the number substituted in or where your cos is, so that I can check that. And then the answer. Okay, so then what can be said about the angle theta, angle between V and W, if your dot product is negative? So there's an example here. Dot product here was negative. This angle was bigger than 90. If you remember back to math 30, and even math 20, okay, cosine is positive, so in the second quadrant, cosine is negative. And so if this is your initial arm, then your terminal arm forms an angle that's bigger than 90 degrees. Okay? So here, if it's negative, then theta is greater than 90 degrees. If it's positive, then it's between 0, so it's less than 90, and greater than 0. What happens if it's exactly 90 degrees? What's the cos of 90 degrees? 0, yep. What's the cos of 0 degrees? So that's why I don't include the equal sign. What's the cos of 0 degrees? 1, okay? So 1 is a positive number. So if we have in our formula the rearrangement of it, if we have cos of 0 here, we would get a 1. So that means this value has to be equal to 1, which is a positive number. So we actually include the equal sign there. Okay, and then this, when I said what's the value of cos of 90, you said 0, so that would be that case there. So this is really helpful. Finding vectors that meet at 90 degrees is going to be really helpful for us as we go on in this unit. So they're perpendicular vectors. Sometimes we call them normal vectors or orthogonal vectors. So be aware, on an IB exam, could be called any of those. Okay, perpendicular, orthogonal, or normal vectors. So if they're perpendicular, then the dot product will be 0, because cosine of 90 is 0. Okay? So in example 3, determine the value of k if u and v are orthogonal. So k is one of the components. We want to figure out what k is so that we get a dot product of 0. So therefore, 5 to negative 5, dot product with 6, k, and 3 has to equal 0. Can you solve that for k? And your components can be fractions, decimals, irrational, rational. So in this case, it's going to be a fraction. Want to do a little sketch for the next one. So vertices of a triangle. So negative 4, 3, negative 2, 1, 2, 5. Those are the vertices of a triangle. It says determine the measure of angle P rounded to the nearest 10th of a degree. So back in Math 10, you would find the lengths of all of them and use the cosine law. Now that we know vectors, really, we just want to know vector R and PR and vector PQ, and then use the dot product definition to calculate the angle in between. So PR, so PR is going to be 2, 5 minus negative 4, 3. Now, what is something that we'll talk about as we go on in the unit, the magnitudes of these, when you're using no, I'm going to notice, forget what this one said right now. Keep them as is. You get confused with the magnitude. So just use those. They are parallel, like you could actually divide each of them by 2 and find the angle in between them. But you would use the new magnitudes is sort of what you have to do. So we'll leave that for now. Just use those as your vectors. So our cosine theta will be 6, that's going to be 12 minus 4 over 40, 8. Rounded to the nearest 10. opposite example. Okay, so if vectors v and w are parallel and in the same direction, what's the angle in between them? Is there an angle in between them? No, it's 0. Okay. If the vectors v and w are parallel but in opposite directions, okay, so then there, the angle, because their tails are together, is 180 degrees. Okay. So show that if vectors u and v are parallel, then the dot product could be the positive or the negative of the product of the magnitudes. Okay, so let's say we use our definition and we have u, v, and our cosine is 0. So this is, first case is when they're parallel. First case is when this one, when theta equals 0 degrees, we have cos of 0 degrees, which is 1. So that's just going to equal the positive product of the magnitudes. Then if we have theta equals 180 degrees, the angle in between them is 180. Cos of 180 is -1. Okay. So, and u and v are parallel in both of these. So there's the positive, there's the negative case. Okay. Okay, so visually describe the dot product on the diagram shown. So we've got two vectors. This is the angle in between them. Really what the dot product is, this is v and w, right? V dot w is the projection of v onto w times the magnitude of w. So what is a projection? So you may have talked about this in physics. It's basically the horizontal component, or the component of this vector onto this one. It may not be horizontal depending on its location, but it's saying, okay, I think about it as, let's say you have a big lamp up here that's shining down onto vector v, down directly perpendicular to another vector w, right? So it's forming a triangle here, and this is the shadow of v onto w. This vector here is the projection of v onto w. So when you see a little letter as a subscript, that means it's a projection onto it. Okay? That's really what the dot product is. But that's hard for us to deal with. So we want to think about, in terms of this diagram, well, what is this side? This forms a 90-degree triangle. So if we think about our definition of cos of theta, back to math 10, is adjacent over hypotenuse. Well, adjacent here is the projection of v onto w. The hypotenuse is the magnitude of v. Okay? So now let's solve for this and substitute it in. So magnitude of the projection is equal to cos of theta over the magnitude of v. Yeah, what did I do?
Is the projection over, like, divided by v?
The definition of the dot product is the multiplication of it.
Well, I think you can make the normal.
No. We're trying to get that, right? So here, this is what the definition is of the dot product. It's this magnitude times this magnitude. So I think in physics you talk about that a little bit in force. I don't know a lot. I can't remember a lot about physics, but I think it's force. This direction of the component of the force times this is work. I'll have to ask Mr. Watt about that, but pretty sure it relates kind of back to physics. So that's actually the definition of the dot product. In terms of that diagram, and back to math 10, in a right triangle, if we've got these labels, cosine of theta is this adjacent side, has nothing to do with W, right? This magnitude, adjacent over hypotenuse. Okay. So, cosine, oh, is that what you're saying? Dividing there?
Yeah.
Oh, yeah. Sorry, I was looking back up here. Ah. No. I wasn't sure which one. I thought you were meaning back up at the top. I'm sorry. That's what you mean. Yeah. Okay. That was my mistake. I told you guys I'm not perfect at all. I make mistakes. Okay, so now I rearrange that and substitute that in. And there you see the geometric definition that we use. Okay. Got that. Okay, so last page. You need to go. We're almost done. Okay, so the last page there has just some of the properties for scalar product. Okay, so reminder that the dot product, if the dot product is 0, the vectors are perpendicular. You can switch the order of the dot product, they're still equal. You can multiply it by a scalar, and it's the same as just multiplying that scalar into one of the vectors or the other. You can take the dot product of, you can use the distributive property basically. And this one's kind of convenient. When you take the dot product of two of the same vector, that means that they are parallel and the angle in between them is 0. So it's really the magnitude squared, because cos of theta is 1. Okay, so last one, we're going to prove that the triangle inscribed in a semicircle is a right triangle. That's a property we learned back in Math 9, actually. So, triangle inscribed. Don't remember Math 9? And that was before COVID, so So, it was before COVID. Yeah. So no excuses, right? It's kind of weird because it's done in Math 9 now. We used to do more circle geometry in usually Math 11, and more to do with not just parabolas, conics, and all that kind of stuff, but they took it out of the curriculum and put all of the geometry stuff in Math 9, and then kids don't really remember it. Get to grade 12, but anyway. remembering this now. So prove that the triangle inscribed is a right triangle. So semicircle, that means this is your diameter here. This O, it's not a great diagram, it doesn't look quite centered, but that we assume that those are equal. That's equal, so any radius of a circle, they're all the same. And we're wanting to use vectors now, rather than any other properties. So this, I'm going to actually, to make it a little bit simpler, rather than using A, C, and B, I'm going to call the vectors just by a lowercase. So I'll call this vector here A. This one I'm going to call lowercase b. This one I'm going to call lowercase c. Okay. So we want to basically prove here that this vector CA dot product with CB equals 0. Okay. So the vectors joined at the same place, the angle between them, we want it to be 90, which means their dot product is 0. So CA in terms of these other angles, so that would be arrowhead there, so that would be A minus C. CB would be B minus C in terms of those definitions that I've labeled. And we'll use the distributive property on that expression. So it's dot product. Don't be lazy. Make sure you have the dots in there. Doesn't have to be big, but because it's not really multiplication, right? So minus A dot C minus C dot B. I just kept them in the order. We can switch the order if we need to. Okay, and then let's look at some of the properties from our definitions here. So vectors A and vector B, they are opposite vectors. Same magnitude, but opposite direction. So you can go, okay, well, vector A is the opposite of vector B. So if I substitute that in for A, then I'll get negative B here, dot B, minus Then, some properties back from that chart. If we take the dot product of two of the same vector with itself, we get the magnitude squared. Okay, so that means C vector dot product with C will give you magnitude of C squared. Same thing with B, okay? And the magnitude of all of these, A, B, and C, are equal. You can even put that up top if you need to, below here, because they're all radii of the circle. Okay, so that means this is going to be these are going to be the same. The order, that's positive, that's negative, so those will add to 0. That means I'm supposed to be doing something. Oh, yeah, line supervision. That's what it's reminding me about.
behave yourselves.
right? Are those rules still, like, do you still have to sit apart now? Yeah?
Except what?
Something about,
Well, I won't say it, I'm recording, so.
okay, so I want to prove that. So really, actually, I should probably not put equals to 0 yet. Now, it equals 0. Okay? So I've now proved that. Okay? You can leave it up here, actually. So we want to prove this. And then, so we've taken the left side. And it equals 0. Okay. That's it for today. So not a lot of work time, but tomorrow is a practice day, so you can catch up on some of that.